Let me introduce you our two speakers. So today you really have a bonanza speaker. You have two. So the one, Laurent, and I can't dare to pronounce his last name. He's got his doctorate in France a few years back. We don't go against back how many years. We made this deal. We just fell on that. And John Leo, also from GE Healthcare, where he got his doctorate at Northwestern in '98. Both in mechanical engineering, but with a focus on mechatronics. They will be talking about surgical navigation. That is what I understand your division does here, especially in Salt Lake. Just not only in Salt Lake, I understand. So without further ado, we'll let Laurent start, and then John taking over after him.
Yeah, so John will translate everything I'm going to say, because my English is slightly broken, as you will hear. So thank you for having us this afternoon. This is a pleasure for us to be here, John and I. Thank you, Gianluca, for inviting us, and thank you, Rajesh, for this opportunity. So, surgical navigation, we're going to go over it together. I'm going to try to describe what it is, but in the context of the industry. So it's not a class, it's more like what we do every day for a living. So I'm sure you heard about GE, right? So GE, we do breakers, appliances, light bulbs, and we do also healthcare. So healthcare is one of the departments. There is, the biggest I would say maybe is GE Capital. Then maybe the second biggest would be like GE Energy with oil and gas. And then we have somewhere GE Healthcare. It's quite big though. It's still 17 billion per year, okay, of revenue, dollars. It's 50,000 employees. And it's everywhere in the world. Everywhere, pretty much. And the headquarters is actually in England, I believe, yes. And we invest a lot. We invest a lot in research and development, and we'll talk more about that. There is a core strength, as I mentioned here, in biosense, and actually how we did that. When I say we, I'm talking about GE, right? It's more about like they acquire companies. Okay, so there is young, creative people that start with new companies, like 5, 10, maybe 20 people. And then GE will be very interested by a company like that and will buy it. And that's exactly what happened to the surgical navigation business back in 2002. This company was based in Massachusetts and existed for at least, let's say, maybe 7 to 8 years before. And GE thought that technology was really interesting and decided to buy it. And so you're going to see the kind of product these guys have done. So before getting there, just what is, GE Healthcare is broad, very broad. There is all those things that we're doing. There is this IT that you may have heard about. Every time you go to the doctor, right, they fill out the form, they go on the web sometimes, they go on their computer for sure, and they fill out everything about you. And that's what we call information technology. And so the software, most of them are developed by GE. Another one that is really big and actually growing is the life science. This is all about future. Today when you have a broken bone, you're actually going to have a plate, right? But the question is, can we use something else instead of an implant to have your bone fixed? This is about this, and this is on the right. And then the left is actually what we're going to talk about today. And we are just the surgery. There's only one word. Diagnostic imaging is a big team. It includes the CT scan, the MRI, the X-ray system, and also surgery, which includes some X-ray and surgical navigation. Okay. So there is a big marketing word, and you may have seen some advertising about it in train stations, airport, etc. It's called health imagination. So I don't want to do a pitch about marketing, just to give you an idea about what is the vision of GE Healthcare. So there's one thing, healthcare, and I'm sure you're aware of that, costs a lot of money, right, to everyone. And one of the main thing that GE is working on is trying to reduce the cost. And how do we reduce that? Well, you try to work by having some product that costs less. How do you make something that costs less and still meet the same quality? Well, unfortunately, you have to work with other countries. Is that unfortunate? No, because you're becoming global, right? so your company is more diverse and more rich in terms of knowledge. You have to increase the access. So what does that mean? Increasing the access is like, think about countries that didn't have access to technology. Well, now we want to make sure that everyone can go and get a scanner, a CT scan for diagnostic. Okay? If there's a cancer in Africa, we want to make sure that we can detect that kind of thing. So we need a CT scan that costs less, that you can have in Africa, meaning that it can withstand some high temperature, some different environmental conditions, but we still want to maintain the quality, right? We're not going to give something that doesn't work well because it costs less. So quality is the third thing, the third keyword here, and this is what all the products are about. Reduce cost, increase access for everyone to have healthcare, and improve quality. If you have any questions, please feel free to interrupt. One slide about the global research. So the reason I put that slide here is because you might be interested in it. GE Healthcare has some, I don't know if you would call that school or lab, but it's very equivalent. Let's say most of you or some of you are PhD students, I believe. Those red dots are actually centers in the world that hire PhD students. And I'm not here to hire anyone, but if you are curious, I invite you to go on the website and search a little bit about that. It's called the Global Research Center, and one of them is based in Europe, Munich, another one in India, another one in China, another one in New York State. The one I'm the most familiar with would be the one in California. It's more than 2,000 engineers. Most of them are PhD people, very smart. Some are also masters, some are bachelor. It doesn't mean that the degree is so important. What is important is what you bring on the table, okay? Your knowledge. And so these guys are not developing one particular product. They are thinking about the future. So let's say, for example, what are the cool technologies that have been developed over there? I think the first plasma screen, John, was developed over there. There was
plasma, organic LEDs, and some stuff we're working on right now. They're known for not perhaps the first work in MRI, but we did a lot of work to bring MRI up to a commercial status. What I did at it was Bell Labs at the time.
I think it was a big one is Lexan, which is a plastic.
Lexan
you know the smart car, that little car? All the body is made of Lexan, so it's very flexible. And that material has been developed over there by some of your peers. So it's always good to know that this thing exists.
Well, I would just add one thing that Laurent's got there. This slide actually happens to be a bit dated. There are 6 global research facilities. There's an additional one in California, and we've just opened one this year in Rio de Janeiro. Each of these sites is comparable to what he has on the right-hand side, usually around 1,000 people employed. So, and this has all changed. I've been with GE just 11 years now, and when I joined GE 11 years ago, we only had the facility in Niskayuna. So I think that's very representative of where we're trying to go. Kind of coming back to our corporate research foundation that Edison had started in upstate New York, and realized that that's our long-term future is what we create.
Thank you. So let's go now to the GE Healthcare surgery business. So where is it? Well, it's in Salt Lake first. So it's near the airport, actually next to the airport. And what is it? It's almost 1,000 employees. On site, it's maybe 500 total, 500 to 600. And we do everything. We do engineering, we do manufacturing, we do service. People, I think we have it over there. So a little bit about that business. So what happens? So first of all, it's very accessible from here. So this is something that, it would be a pleasure for me to, if you want to have a tour or something like that, you can come and you can organize that. First of all, I mentioned to you that the surgical navigation business was acquired by GE. Well, it's exactly the same that happened to actually the OEC business that became the surgery business. So OEC stands for Orthopedic Equipment Corporation. And this is the one on the top. In 1946 it was created. Then they introduced the first C-arm in the US. What is a C-arm? We'll go over that. I have big pictures of this. But this is, think about an X-ray system that exists in the operating room. After importing the first system from Italy, actually, they decided to build their own. It was in 1977. It was a great success. A lot of surgeons loved this system because it was very easy to handle, and they could actually, make sure that it was very used in an emergency room to make sure that, trauma cases were well taken care of and quick. GE thought that business was amazing, so they decided to buy it, and it became GE Medical System, surgery business. Again, in 2002, they acquired a surgical navigation company, which was named VTI. And so, in 2006, something interesting happened, and we'll go back on that too. All the medical and the healthcare industry is regulated by the FDA, the Food and Drug Administration. What happened in 2006 for us here in Salt Lake City is that they came, the FDA agent, they came and they said, well, you guys know what, you're not compliant anymore. And we've been telling you that before and you didn't fix it. So now, we're just going to shut down the plant. And it's called a consent decree. And this is what happened in 2006/7. This is why you see this. This business was not making any money anymore in 2007. I'm not talking about GE Healthcare, just the surgery segment. So instead, we went from $500 million to almost nothing. So since then, we're kind of back on track now. We went through many audits, and then the FDA said, yeah, I think you guys fixed it well. We're happy with what you did, and so therefore now you can sell. And this, this is real, actual number. I think today, in 2012/2013, we're back to that. Our forecast is to go higher, of course. And but this is pretty much the story of the surgery business here in Salt Lake City. Global footprint, I'm not going to go back on that, but it's just about the surgery. We're trying to be global, so it's not just Salt Lake City. It's also Europe and Asia, and of course South America, and so forth and so on. So what is our vision here? So we mentioned about the GE Healthcare vision, which remember those words: increase, decrease cost, quality, and access. Well, there is also something else. Let's say you have to go for surgery at the hospital, and then you have two surgeons. One is telling you, well, I can do that for you, and then you have, you'll stay with us like for 2 weeks, and you have an incision that's going to be big like that after the fact. And another surgeon will tell you, well, I can do that, yeah, sure. You'll be out from here in 2 days, not 2 weeks, and your incision will be big like this. So then you're like, what does that mean? I mean, I'm not going to get the same treatment. So there is actually something happening now, which is called MIS, minimal invasive surgery, where it's a trend. It's not a trend, I mean, it's a new technology that allows that. But surgeons are now going toward minimal invasive surgery, meaning you reduce the incision. Okay? So when you reduce the incision, the problem is you don't see what's going on inside. So how do you see it? Well, you take X-ray, right? So that's why the C-arm system that is used in the operating room is so useful, because it's actually the eyes of the surgeon. Because since you cannot see through the skin, we take X-rays and then we see through the skin. So we can see bones. We don't see soft tissue with X-rays like that. They're not powerful enough. But we see pretty well the bone. I have some pictures I'll show you. So what's happening is that we're going from something which is called invasive, where you have a huge incision, where you stay a longer time at the hospital because you have to recover from that. I mean, it's, when you do a good wide incision like that, all the soft tissues are pretty, damaged in some ways, and they need some time to get back together, especially the muscles. It costs a fortune because you have to stay 2 weeks at least. And so now what we do is we go to a less invasive, smaller incision. It's more cost effective because you stay only 2 days. And the other thing we'll talk about that. I mentioned here, the dose thing. So we'll talk about that again, but I think here we're talking about X-ray and radiation. So again, small incision, we're saying it's a huge benefit. Okay? There is plenty of papers publishing about that. This is a trend that started to happen in the 2000s. And as you can see here, there's some example. Okay, I tried to reduce that to the minimum. I hope not. This is a little bit bloody, but that should be fine. It's just to show you, this is when you do a big incision, this is when you do a little tiny incision. Okay? So this is pretty much all the, not all the spine, but all the lumbar spine from here to there. And here it's just like 3 tiny holes to do the same surgery, which is quite crazy when you think about it. So spinal fusion is now going toward this. That number actually is reduced reducing dramatically. We're not at 75 anymore. We're around like maybe 30, 35%. And you can see the benefit of it on yourself. The scar is much smaller. You're suffering less because your muscles are less damaged. Same for your nerves and all the rest. But some of the surgery, don't take me wrong, some surgeries you cannot do. Okay? Some you can, some you cannot. But this is just an example of the one we can do. And what I would remember from that slide is that really, this is where we're going. We're going toward something that is less invasive for the patient. Okay? And we are, as you can tell on the top, we're still in line with the G healthcare vision. We're trying to reduce this cost and improve quality. So, the surgery business, I mentioned the C arm. This is what it is. It's really a C, and it's attached to an arm. Okay? So that thing actually goes around the table, the surgical table, and can rotate around it manually or motorized. There's different features. You have this workstation. That workstation is just a computer. And what it does displays actually the information from that system. Here you have the X-ray source, and over there you have the receiver. So the body is in the middle. We are, as patient, in the middle. And then on the screen here you see your bones. Well, the surgeon, let's say. And that's the kind of application that these systems are typically used to do vascular cases, okay, to repair if there is any problem, any concern in arteries and stuff like that with catheters and wires, etc. We do orthopedics with all the broken bones, and we do spine, as we mentioned earlier. Spine cases sometimes takes, for scoliotic spine, it can take up to 6 to 8 hours. So it's a long time of long surgery. What is critical for us is the image quality. So the surgeon needs to see everything, all the anatomical landmark, because we mentioned it, right? The incision is smaller, so he doesn't see what he's doing. So he has to take more X-rays. The ease of use is important because you don't want to have a system that an engineer thought about that is great on engineering standpoint, but so complex to use, right? It's like, I wouldn't compare that to the iPhone, but it's like the iPhone is so easy to use that everyone can use it. My mother can use it. She's happy with it, okay? If I get her another type of phone, it would be difficult for her. It's the same thing here. The surgeons has time for you, not for the technology. So they have to really, the technology has to be easy, okay, and provide what they need. And that's what we're looking at. Next slide would be another product, and this is really the navigation system. So it doesn't take X-rays. It's just a computer. Well, it's a little bit smarter than a computer. It has a little bit of other stuff. And John will describe what it is exactly inside the box. But the application are almost the same. So what we do this particular product is called the IT3500. And what it does is it does surgery on cranial cases. So let's say a patient has a tumor in his brain, and back in like maybe 20 years ago, what used to happen is that you would take a big knife and just open the head, open the skull, right? So what happened today is that actually we do a tiny hole, and then we use that system to get in. And that's what we call surgical navigation. So instead of, we could take X-rays, right? But what we want to do actually is to use this instead. And why? Because there is something that is becoming a problem. The surgeons are going toward minimally invasive surgery, MIS, but they take more and more dose, more and more radiation with their X-ray system. So they're starting to be concerned by that because they have like maybe 2, 3, 4, 5 cases per day, and it's always radiation. Some of their peers are dying of cancer because of radiation. And so now what's happening is that we have to find something to help them, right? So this is where it comes. This navigation system allows them actually to virtually see where they are. So it's pretty much like a game, you would think, like the way you display the information. But the way it works is very simple. You use a pre-op scanner or intra-op images, but you use only one. Only one. You only take one shot. And then what we'll do, and you'll see it on the first slide, is that we display virtually the position of the instrument within the body. So it's an overlay on the anatomy. Few words about the regulation. So I mentioned earlier that our business was in consent decree back in 2007. So something we the FDA said you cannot ship anymore. So what does that mean? I mean, why is that? Well, the first thing we have to respect when you are, a medical device company is you have to follow the rules. You cannot just say, hey, I'm a medical device company and I'm going to sell your product and please, doctor, use it on this patient. No, it doesn't work that way. You have to follow the rules, kind of. The rules are, first of all, the good manufacturing practice, GMPs. I don't know if you ever heard about that, but this is a little book. It's called 21 CFR Part 820. It doesn't tell you how to design a product. It just tells you what you should be careful with. So it tells you, for example, you need to have requirements. What is it? Requirements? Well, the system shall be able to accurately place a screw within 3 millimeters. Okay, that could be a requirement. And so then you have to test it. So someone needs to physically test that requirement. And then you have to validate it, meaning you have to do some pair lab or phantom lab to validate that, yes, a surgeon can actually reach this accuracy. So, and this is what we call design control and so forth and so on. And you have to follow these in order to be a medical device company. So it's not like a gaming industry where you can just come with a game and give it to everyone. Here, think about it. This is a tool that will be used by a surgeon in the operating room. So it doesn't follow the same rules because the life of the patient relies on that. And so I'm not going to read all those things, but there is a scenario, there's a workflow to follow. And the first step is actually when you have a new product, it's called the 510K. You need to file the pre-market notification, not the pre-market, the pre-notification, 510K here, that actually will be sent to the FDA, and the FDA will tell you, yes, you are clean, you can go ahead, or no, you have to work harder on this. This is not a good product. You're not ready to sell. So EM stands for Electromagnetic Navigation Technology. So now we're getting into more like the content of the presentation. What we've been going through earlier was more like the business aspect, okay? And what is GE? What is GE Healthcare? Is there a regulation? Yes, there is. And so now what is really surgical navigation? So I mentioned it briefly, but this is what it is. So before, you would have seen for a cranial case, an incision like this one was pretty common. I mean, you would see, maybe not in the eye, but at least just the skull itself would be cut this way to actually access a tumor. Nowadays, what the surgeons are doing is actually, instead of doing that, they're going to just do a tiny hole, and then with that hole, they're going to have a pointer that's going to go through the hole. But they still need to see what's inside, right? So how do they do it? Well, they use a pre-op CT scan, for example, and then they use a pointer, physical pointer or instrument. And the way it works is that this physical pointer is actually registered with the anatomy, which is registered to the imaging. So you have this image, which is a real CT scan of the patient, with that virtual representation of the pointer. And since everything is registered, when I move this moves relatively to the anatomy. So I'm a surgeon, I have my patient in front of me, and I looked at this screen, and the screen tells me where I am in real time. And so what is important there is the accuracy, right? You need to make sure that, hey, when I touch that point, this is really the point I'm touching and I see on the screen. And that's key. That's why when we do verification and validation, it is so important to say our accuracy level is 1 millimeter or 2 millimeter or 3 millimeter. So I hope this is clear. In few words, the way we tell about surgical navigation, just say it's a GPS for surgery. And it's true, it's a GPS. It tells you, hey, that's the entry point and that's where you need to go. So it gives you the trajectory and the position of your instrument in real time. And there's a slide for me, so what are the benefits? Well, you heard it earlier, I talked about the dose, the radiation dose. Since this is virtual and this is updated in real time, I don't need to take as many x-rays anymore. I just use my simulation here. So that green line is actually, when I move my pointer for real, I can see it moving and I can see it slicing my data set for the CT scan. And so I know exactly where I am in real time without having to dissect the patient or without having to take another x-ray. So big time, this word is back, MIS, this acronym I should say, minimum invasive surgery. So yes, we do enable that. Because thanks to this virtual representation, actually you don't need to do big incision anymore. We can do 3D images, 2D images, this is 3D. Think about it, the surgeon thinks in 3D. When he does something, he does it in 3D. The problem we have today is we are providing those technology. It's great, but it's 3D, but it's actually projected on a 2D screen. So some of the surgeons are now thinking about future. Can you make me something in real 3D? You know? And I'm not talking about those, you know, the optical glasses and that kind of stuff. It's more like a feeling of really going around the model, around this virtual world that is a real 3D representation. Surgeon confidence, well, it's key. If the surgeon doesn't trust the system, then he won't use it. So you may have done the coolest design, the best-in-class user interface, something that you're very proud of. The problem is it doesn't work. It's not accurate. So the surgeon will be like, yeah, super cool. I'm not using it. So that would be the best problem, right, to solve. And that's what we're trying to avoid. So again, nav is just a net to the surgeon. It's not something that's going to tell him, hey, you need to go there or there or there. No, the surgeon decides, he owns the surgery, he knows exactly what to do. This is just an information that tells him where you are. It's like a GPS in your car, right? If the GPS tells you it's on your left now, and you know by heart, it's not on my left, I know exactly it's the second left. You will decide to fool a GPS and go second left. It's the same story here. Surgeons and GPS navigation is just a net. Okay, I think that's what we have on the business side, and quick introduction to navigation. And now we're going to get deeper into what is really surgical navigation, what are the components, because you will see it involves a computer, there's also some other stuff, and of course what are the applications and how it works. John?
Thank you, Laurent. So the commercial space, we want to talk a little bit more about the history of this technology, these systems, these companies. I would say 20 to 30 years ago, surgical navigation started out in academia using electromechanical means for localization. And the electromechanical was a couple different types. So first off, there was something that's depicted here, which is a passive articulated arm with encoders on it, and you get an architecture which has a full 6 degrees of freedom for measurement, or 5 degrees of freedom if you can't measure around the axis of rotation of the instrument itself. And you can really navigate, so putting a needle into the body. There was also a lot of work done with industrial robots. The Puma 260, maybe you have one here, maybe you don't. As the industrial robotics faltered in the 70s and 80s in the US, not so much in Japan, there was a lot of surplus robots. Universities picked them up, universities started doing things with them that they were never intended for. So some really neat stuff, Puma 260s, Puma 560s, things of that nature that has kind of spurred this. However, the surgeons have said, I don't really want the constraints of having to interact with a mechanical device or telling a robot to go ahead and do surgery. So can't you give me something that works freehand? So from the areas of passive tracking, we've got optical. So what you're most familiar with this today would be maybe in a biomechanics lab or in Hollywood for the green screen superposition of actors and tracking them with a bunch of white spheres. So this is essentially the same idea. Is that you outfit an instrument either with active LEDs or some sort of reflective marker, and you can pick up and calculate the full position and orientation of that object. The problem with this, as you can see from these imaginary lines of sight, is that if the surgeon dips his head in the way, the connection is broken. So there's a line of sight constraint. So the third generation that we're looking at is actually electromagnetic. And this started, I would say, in the mid to late 90s to become a very viable technology for deployment in the surgical navigation space. All right. One of the caveats, however, is that it is sensitive to distortion from certain metals or conductive surfaces. So it's not without some trade-offs, just as as the optical systems have. So Laurent showed you a system that was a big box on a computer screen. So the question might be, well, what's inside there? So first of all, and here's a picture of that. So there's a system design aspect of building, having a computer in there, having a tracker, a real-time tracker of some sort. The sensors themselves, this blue one here actually creates an electromagnetic field in the vicinity of the patient, which is very a refined electromagnetic field that we understand well through the characterization process, calibration process of the field. And then these are little snap-in sensors that can attach to the surgical instrument, that can attach to maybe the imaging device, and we can track all of that relative to a patient-mounted transmitter. So now, just as Laurent said, this is GPS. When we think of GPS from what the government funded in terms for military applications back in the 80s, we think of a satellite constellation that calculates latitude, longitude, and very roughly your altitude or elevation. But that type of GPS was not very useful, A, because of limitations in the commercial space, and B, because if I have in my car a readout of latitude and longitude, I really don't care. That doesn't help me. What really happened was somebody said, let's go and get all this GIS information, this mapping information, and let's meld the two. So I can take the latitude and longitude, superimpose it on a map, and now I have something very, very useful to me in the car. So I have my view out the window, which is the immediate steering and making sure I stay in control. And then in terms of my objective, getting down to Ogden or something of that nature, I have a map right there in real time to tell me where I'm at, how many minutes I have to go, how many miles, where my next turn is. So that software and that melding with the imaging technology is critical to creating what we really call navigation. Devices, there's either interfaces or instruments that we have to design ourselves. And finally, all of that in the context of what's the clinical application? What are they trying to achieve? Just putting a sensor on it and saying, here, doc, you can track this, they'll say, I don't care, right? So what you want to do is find out that their problem is, well, I really don't know where this bone is relative to this landmark, and I'm trying to put a screw in. So your software has to be smart enough to help depict that in the correct way. So it's not just a generally applicable technology, there's a lot of customization on a per application basis. Let's talk a little bit more about the commercial space. What you have here on the left-hand side are all of the companies that play in the surgical arena. So you've got anywhere from Brainlab, Stryker, Medtronic, which are really kind of the biggest players we've got, down to some of the smaller or markets that are a little bit different, GE or Siemens. But the technology itself, the tracking technology itself, is mostly off the shelf. So in the case of Brainlab, in the case of Medtronic, they buy from a Canadian company called NDI. In the case of Stryker, it's in-house. However, they actually bought a company, a startup. Okay, that's a little hint, you might want to do a startup. They bought a startup back in the mid-90s and just brought it in-house. So they did not develop it natively. We use Paul Hamus, or had used Paul Hamus with GE Healthcare. There's a competitor to them called Ascension. Actually, I see you've already depicted that we're moving to Ascension. So that's really, in a nutshell, what that is that while there's opportunity to work on that technology, realize that there's a relationship here in how the technology is used commercially. So Laurent already talked about this a bit. The only thing I wanted to clarify on this slide is that where we have a system where navigation is integrated with real-time X-ray, one of the applications tends to be spine. However, in a case where you might import a CT scan or an MR, you would use a standalone system such as this, which doesn't need the X-ray capability. So that tracking technology and the clinical applications, the software is deployed into both of these systems, but the applications are different, so the software becomes two. Okay, a nav system architecture. Here's a very simplified diagram of what's going on. What you see on the screen is a depiction of, say, the spine, and the arrow represents the trajectory of a surgical instrument. And if we work back down from what the user sees, the display is driven by a PC, which is connected simply via USB to a tracker. The tracker is doing nothing more than driving the transmitter or RF generator, and then also making the measurements with the sensor gauze. All while that's going on in real time on the patient. And for anybody involved in mechatronics or robotics, this would be very familiar. It's really just about working in 3D space, coming up with the full transformations from, say, an imaging space out to the patient space, which is defined by the attachment of a transmitter, generating that field, and then the instrument, which has a sensor, or essentially a three-dimensional reference frame attached to it at the center of the sensor. And in order to go from the imaging space via this vector to a point, say, in the sinus, we can get there through image space, but then the other piece we have to do is be able to go from image space, register to the transmitter in some way. This is usually some algorithms that do this. And then also the direct measurement of the tracker, giving us the transmitter to the receiver relationship. So, oh, you had it animated. So there it is. I guess the last piece is, even though I can go out to the sensor, that doesn't help me unless I go to the tip location. So there's many ways to do this. I think the simplest way to think of it is, if I take an instrument, can I borrow your pencil here? So if I take this as an instrument, I have a sensor located on the distal end of it, so back here, I'm actually on the proximal end, near my hand. If I want to know where this is, there's some simple things you can do. One of the simplest you can do is just process on a sphere, make all those measurements, and then take the data and fit it to a sphere. That defines where your sensor is. So simple concepts like that actually make a very usable system. Here's another example. Outside of the sciences, but this one's involving X-ray. So here you have the transmitter attached to the spinous process of a vertebral body. The surgeon would actually like to define a trajectory into this bony part where they can place a screw. So if you remember the previous diagram we had, we've got all of the relationships of going from the imaging space to the transmitter, to the receiver, and again down to the trajectory that you're trying to avoid here. The registration techniques for using two-dimensional projective transmission images, such as a X-ray, are very different from the full 3D registration that you can do with a CT, for example. So fun problems. And as I said, on the X-ray side, it's in real time, so we have to deploy some technology on the C-arm that Laurent described. So one of the first things that you need to do is know where the C-arm is, the X-ray machine is relative to the patient. So you can see that's depicted by having a sensor on the C-arm and being able to measure relative to the transmitter that's located on the patient. There's a couple of things that you need to do with an X-ray machine to make the X-rays usable. So the first is, you need to understand the conic projection. So you can imagine that this triangle, or this cone, the projection, depends on any mechanical deflection of the C, any kind of translation of the source relative to the detector. And this all has to be calibrated and well known for the system to operate in its augmented reality fashion. The second thing is that the image detector is depicted up here is actually an old image intensifier, which is basically electron optics, which are very sensitive to distortions from the Earth's magnetic field. They have a spherical input surface, there's a pincushion distortion to the image itself. And so we have an array of fiducial markers, or reso marks, just as they used in some of the Saturnian voyages of the Voyager missions. The Voyager missions used a similar technology to actually linearize the images that came back digitally of the moons of the Saturnian system. So it's the exact same technology deployed on today's medical devices. Electromagnetic basic principles of this is that we've got, as we already said, we've got a computer or a tracking device driving the transmitter, so applying a current to this transmitter, and then actually a DDA making measurements off the receiving coil.
Just
Give me a time, yeah, okay, yeah, and that's 5 minutes late, so let me wrap this quickly. So I think the key thing to know on this is that a single coil will only give you 5 degrees of freedom. The degree of freedom we don't get is the spin about the center of the coil itself. I'm sure you're quite familiar with this. So we use a triple array of coils in order to get full 6 degrees of freedom. It's redundant, and we take advantage of that. Okay, this is our obligatory Faraday's equation induction. So you should see that the design of these is dependent on a couple of things. One is the rate of change of the flux. Other is the effective area of the coil. So this is the cross-sectional area of the coil plus the number of turns, as well as the magnetic field. And all of these things play into how we design our sensors. So quickly, we've got the first one, which is the triple coil array. But we do have some new ones. You can see those are actually about the size of a dice, right? So with the little pips on it, about 1 centimeter on each side. That's great, and we can track accurately. However, it requires it to be placed on the proximal end of the instrument. It'd be much better if we could replace something at the tip of the instrument, which is more where they're trying to accomplish the surgical intervention. So we have something like this that we're working on, which is what we call microcoils. So those are on the order of 8 tenths of a millimeter, 800 microns, 900 microns, about a millimeter in diameter, and perhaps about 5 to 10 millimeters long. I think Laurent went over some of this, but back to the cost, quality, access, and what are we trying to do. There is a paper where we studied some of the benefits of using a fluoro-based system. And what you see is that in a case of 122 MIS cases, about half of which were navigated, the other half which were fluoro, we saw things like the surgeon's opinion that the trajectory that he followed was better, but a 62% versus 40% favorable rate there. Lumbar placement, we did these on cadavers, so we could actually do a dissection and evaluate after the surgeon did the intervention. And we looked at, for our definition, what a breach looked like, which means the screw coming outside of the bone, potentially impinging on a nerve or on a blood vessel. We saw 16 versus 42. So a number of these are not an issue. So even though that sounds like a very alarming number, it's common in surgery. As long as the breach is in a safe zone, it's considered acceptable. Probably most significantly is actually reduction in fluoro, as we become more sensitive to X-ray dose and non-ionizing radiation. That the radiation necessary is perhaps a 75% or almost a 4-fold decrease. I think that's basically what I have. Yeah, there's the question slide. I think the only other thing that we wanted to note was that there's a lot that goes into the usability of these devices. And this is depicted a bit through the screen layouts that you see here. But the key is the visualization. One of the struggles that we have is with how do you make all the controls. And so what you can see here is that there's a lot of buttons, and we have a touch screen and they can walk and play with these. But the surgeons are very apprehensive to go do anything like that because of breaking the sterile field and the additional time that it takes. So when we get into things like connect systems or other voice recognition, gesture recognition technologies, these are things that have real clinical benefit if we can get them to be simple enough to use in a clinical environment. And we get away from things like so much touchscreen information for us. With that, I think we've got only a few minutes left. If you have any questions for myself or for my colleague Laurent, We'd love to hear them.
Great, thank you, John. Questions for our speakers before we put us out of the room?
What's the duration of X-ray exposure to X-rays during the surgery?
What is the duration of X-rays?
Yeah. And
So-
is it harmful over longer periods? Because surgery could last for hours maybe.
Right, it's a great question. So I'll take a stab at it, and Roger can add a little bit. It really depends on the type of surgery. So when you look at these spine cases, you might accumulate a total of 1 to 2 minutes of fluoral radiation. And because we're using a detector that it's really like almost like night vision, right? So a lot of amplification of signal to get something usable out. So it's still fairly low dose. You might get 1 to 2 minutes there. That's again in the spine case. If you go to something like cardiac surgery or something that's interventional with vessels, that could be a half hour of X-ray during a placement of a stent or trying to do some sort of non-invasive intervention in that sense. So great question.
I have a side question then. So, what about those people around? So, do they get the dose of radiation or some of them too, and they're constantly exposed to that?
Absolutely, absolutely.
So surgeons are fine with that, and nurses.
And they're not fine with it. That's actually one of the major selling points of navigation in anything that reduces the need for ionizing radiation for imaging is that it's an occupational hazard. And the scanner and anything that they're getting to the thyroid or can be detrimental. So they typically wear heavy lead vests, leaded glasses, a thyroid collar. They can even wear caps that are lead. And all of this is bulky and hot. And imagine wearing an extra 20 pounds, 30 pounds during a 4-hour case. And you just get very tight. So a lot of times they'll take that off and then have to bring it in. Everything is just a disruption to the surgery. So anything we can reduce, they can reduce the need for X-ray is valuable.
Any other questions? If anything comes to mind, you can, I'm sure, shoot us and for me and me to them, and so on. And so let's thank again John and Laurent.